Thank you. So our next speaker will talk about multiparty types. Thanks.
Okay. Yeah, thanks for the introduction. This is joint work with David Castro-Perez and Francisco Ferreira from the University of Kent and Royal Holloway. I'll proceed in two parts with this talk. In the first part, I'll cover the second half of the title, namely the existing work on multiparty session types. And then in the second part, I will cover the first half, namely our contribution in this area. But before I get into any of the technicalities, let me first say a few things about the general context in which the work took place. So, in general, I think the long-term research goal here is to make concurrent programming easier. And the kinds of concurrent programs that we are looking at in this particular paper are those where we have a bunch of processes that communicate with each other using channel-based message passing. Okay? And for this class of programs, we want to help programmers reason about safety and liveness properties, and in particular those that pertain to the message passing behavior that the processes engage in. Okay? And the way that we do that is by providing programmers advanced type systems that can take some of the burden for these programmers. This is, in very broad strokes, what the paper is about. Now, let me be a bit more precise about which problem in particular we want to help programmers with. So, imagine that we are programmers, and after doing a lot of work, we have written both a specification and an implementation of our concurrent program. And I'll assume that our specification consists of at least 3 pieces of information. First, we need to know something about the processes that this program consists of. We also need to know something about the channels between those processes, and finally, we need to know something about the expected message passing behavior that the processes engage in, or in other words, the communication protocols they need to comply with. Now, given these 3 pieces of information, one of the complicated challenges that we now need to address is somehow prove, or at least convince ourselves, that this implementation is safe and live relative to the specification, where safety means, informally, that bad communications never happen, while liveness means that good communications eventually happen until the program possibly terminates. Okay? Now, over the past 50 years, I think many techniques have been developed to help programmers with this, and as I mentioned before, we are looking at type systems. Okay, so the idea behind these type systems is that they will be sound in the sense that if each of the processes is individually well typed at compile time, then we want to conclude that the parallel composition of those processes is safe and live at runtime, right? That is the goal. Now, in general, this is called behavioral typing, and one particular flavor of behavioral typing is multi-party session typing, and that is what we look at in this paper. So, let me try to explain how this works on one slide. Our starting point is that we have this implementation and the specification, and in this very simple example, our implementation could look something like this, right? So we'll have 4 processes, which we'll implement in terms of 4 terms in some kind of programming language. Now, because this example is so simple, our language, in this case, needs to have only 2 primitives, namely sends and receives. Sends are represented by the exclamation mark, receives are represented by the question mark, right? So Alice starts by sending value 5 to Bob, and Bob correspondingly starts by receiving a value from Alice stored in variable x, which is supposed to be of type not, so it's a number. Okay? I'm also using this square bracket notation, which is just syntactic sugar for multicast, essentially, but the details don't matter so much. Okay? So we'll have terms that implement the protocol. Now, we also need to have a type that specifies the protocol. And again, because this example is so simple, I can write the type using only one kind of type constructor, and it looks something like this. Okay? We have this arrow here, which means, A arrow B means, a message is communicated from Alice to Bob, right? And the type of the message should be a number. Okay, that's our only type constructor. And then on the right-hand side of the semicolon, we have another type that specifies the continuation of the protocol. Right, this is the idea. This is our starting point. Now, if we want to do multi-party session typing, we now need to proceed with 2 steps. In the first step, we'll extract from this total specification at the top a partial specification for each of the processes that defines exactly what that process is supposed to do to comply with our protocol. So for instance, for Alice, we have this partial specification that says that she needs to send a number to Bob, and for Bob, we have something that says that he needs to receive a number from Alice, right? There is this duality here. Okay? Now, normally in the session types literature, we call these total and partial specifications the global type and the local type. And the process of extracting the local types from the global type is called projection. Okay, fine. When we have projected this global type onto each of the processes, so we have all our local types now, then the only thing that remains is to type check each of the processes against its own local type. And this is essentially by sort of syntactically matching the structure of the type against the term. Right? If they somehow correspond syntactically in this way, then we can conclude well-typedness. Now, in this very simple example, we have only 4 of those terms, but in general, we can have any number of processes. Right? So then the picture looks like this. We start from a global type, do our projection to obtain the local types, and then type check the processes. Now, suppose that we go through all of these movements. What really does that give us? Let me be more precise about what time soundness formally means. And I'll do that in terms of these classical notions of progress and preservation. So the progress theorem could be formulated something like this. Assume that we have some predicate phi on collections of local types. And it doesn't really matter at this point in the talk what exactly phi is, but it is apparently something that we need. So, okay, fine, we have it. We'll also assume for progress that we have the parallel composition of the processes, represented with this capital pi operator here, that is not yet terminated. Okay, so down arrow here is the termination predicate, but they're not yet terminated. And we'll also assume that each of the processes is individually well-typed. Then we can conclude that there exists a bunch of next processes such that the current processes can make a transition to the next one, right? So they really can make progress. Now, similarly, we have preservation, for which we apparently also need to have this phi property. But now we assume that we already know that the processes can make a transition, and they are still well-typed. And then we can conclude that there exists a bunch of next local types, such that each next process P prime is typable by this next local type, right? So typability is really preserved by these transitions. Now, the interesting thing here is that these next local types, they don't sort of appear out of thin air. There turns out to be a very nice, interesting relation between the next local types and the current local types that we start with, which is typically represented through a transition relation. Okay, so we take somehow a kind of operational view on these local types. We interpret them basically as automata or as state machines. And then we have this transition relation defined for our local types that we can use to synthesize these next local types from the current ones that we already have. Okay? Okay, so progress and preservation, this is what we all can prove, and then we combine them, and then we have type soundness. Okay. Now, in principle, this is all fine, but the practical applicability of these theorems crucially relies on our ability to establish this phi property. And for a long time in the community, we sort of assumed, or we thought, that we get this property essentially for free. We thought that if we start from a global type, do our projection, then this phi property is sort of entailed through this whole process, or by this whole process. So we have it by construction. Now, unfortunately, a few years ago, in POPL 2019, Skalas and Yoshida show this is, in general, not really the case. Right? So for the simplest of multi-party session type systems, yes, we have it, but if you make it a little bit more complicated, a little bit more expressive, then you lose this satisfaction of this assumption. And so I guess I'd like to emphasize that the theorems, they are still true, but they're applicable just far less often than we originally intended them to be, so to speak. And so this is somehow the current state that we are in. We have this original approach from 2008, which is basically what I've been talking about so far. And then 7 years ago, we have this observation by Skalas and Yoshida that say, yeah, okay, but this phi property is not really entailed by projection. And so what they do in their paper, they also propose an alternative approach that sort of fixes this situation. And I will call this approach the less is more approach, because the title of this paper is Less is More. So colloquially in the community, when you talk about the less is more paper, then it's generally understood that it's about this paper. Okay, fine. So the idea behind this less is more approach is that given this observation that projection does not entail phi, yeah, why would we do projection at all? Right? Can't we just skip this whole layer of global types and projection and do everything just completely in terms of the local types? And that is what Skalas and Yoshida propose. So they have these local types, they have a separate proof method to establish this phi property for families of local types, and then they formulate the whole meta-theory around this thing purely in terms of those things, without global types. Now, this has been a very influential paper in the community. So over the past 5 years, I think many people have adopted this approach. It really is, right now, I think, the state of the art. So what we add to the state of the art in this paper is essentially another solution to the same problem. So we still need to deal with the fact that phi is not entailed by projection, but instead of saying we get rid of the global types and do everything in terms of local types, we explore the idea of keeping the global types and removing this intermediate layer of local types. Okay? If you do that, we still don't need projection anymore, and as it will turn out, we also don't need this phi property. So that is essentially what we want to do in this paper. Now, why would you want to do this? What is the advantage? Well, it turns out that by doing so, we can somehow recover the compositional nature of this whole type-checking approach that was part of the original paper, but that was somehow lost in this less is more approach. Because in this less is more approach, in addition to just type-checking your processes, you also need to do separately a kind of global analysis, right, on the state space of your local types, which is sort of non-compositional in nature. Okay? And so with this approach that we propose in this paper, we do have a kind of compositionality. So, to summarize the contributions, we have a new multi-party session type system where we type check processes directly against global types instead of projection and local types. And then we show that by doing so, we attain the same level of expressiveness as the less is more approach by Scalas and Yoshida. So what they have in their paper, they have kind of a benchmark set of example protocols of which they show that they are the first ones that they can actually support them. And we show in our paper that we can support the same protocols, but in a compositional fashion. That would be the novelty in this respect. Okay, so that's one thing. Then we zoom out a little bit, squint our eyes, and then it turns out that there is a kind of a nice generalization of this type system where instead of using global types, we look only at the transition relation of the global types, or in other words, labeled transition systems. And so what we do is we formulate the whole meta theory purely in terms of those labeled transition systems, LTSs, and then separately we show that this general case, in a formal sense, really subsumes the special case. So if you were to use global types, then yes, you also enjoy the type soundness result that we prove primarily for well-behaved labeled transition systems. Okay, now these are all the, let's say, theoretical contributions of the paper. All of this is supported by an artifact in which we have a formalization of all the results in Agda. So all our proofs are machine checked. And we also have a proof of concept implementation of the special case. So we have a Visual Studio Code extension with an LSP server that runs a parser and a type checker, and then you can sort of in a toy implementation language, you can write types and terms, and you get syntax highlighting and red squigglies if you make type errors. So that's very nice to experiment with the theory, I suppose. Okay, now what I want to do in the rest of the talk is just try to convey the main intuitions behind the techniques that we use. Okay? So, the goal here is to have a type system, multi-party session type system, where we use, or where we type process terms directly against global types. That's what we want to do. And it turns out we need to proceed in 4 steps. The last step that we do is prove progress and preservation, which are now formulated like this. It's essentially the same as what I showed you before, except that we now have global types as our types, and we no longer need this phi property. Okay? Now, if you look at the formulation of these properties as progress and preservation, then we can identify 3 things that we need to define before we can start doing any of the proofs yet. Namely, the operational semantics of the terms, the operational semantics of the types, and the typing rules that link everything together. Okay? And so in the paper itself, we have lots of these kind of inference rules. I don't want to show all of them today, but I just want to show you the simplest ones for the simplest features of the language, just to convey the general idea, right? That is the idea. So let's start with the operational semantics of the terms. I'll show it here only for individual sends, individual receives, and communications. Those are the most interesting ones, perhaps. So, for instance, on the top right, we have an output process, right? And what this rule says is that the output process can make a transition to the next process P prime if we can evaluate E, which is the message that we're sending, to a value V. And then the label on the transition is a representation of the send action that's being performed. So PQ represents here the channel from P to Q, and V is then the value that we're sending. Similarly, we have such a rule for receives. And for communication, right, if we have an output process and an input process, and we put them in parallel, then we basically just synchronize their transitions. That's what's happening here. Now, I should emphasize, these rules is a completely standard. This is just concurrency theory. Our contribution is not on this part, but I mean, we need it, so I needed to mention it here. Similarly, we have an operational semantics for the types, which in its simplest form looks like this. So we had this type constructor for a single communication with a continuation G prime. Well, again, we can make a transition to G prime. And the label in this case represents the whole, or specifies the whole communication that is allowed, so to speak, by this type. What you should notice now is that let's say, the structure of this transition label for the type is the same as the structure of this transition label for the parallel composition of the terms. And this is important because in this way we can sort of link the behavior allowed by the type to the behavior actually realized by the terms, right? So this is important if we want to formalize safety, okay? Now, finally, we also need to have some typing rules, and they look something like this. So on the bottom left, the typing rule for output processes says that this output process is typable by G if from G we can synthesize a next global type G prime such that at least the next process P prime is typable by G prime, right? So we have this inductive application of the typing relation. But also, of course, we need to know that the send action itself complies with the communication that the global type prescribes, right? So we need to have that the receiver Q is the same and that this message E that you are sending is of the right type T. Okay? And if this is all the case, then we can conclude that this output process is well typed by G. Now we have a similar rule for receives, and then if we want to type the parallel composition of an output process and an input process, we just type those processes individually, and then we can immediately conclude the typability of the parallel composition, right? So this is the compositionality that we were actually looking for. Now in the paper we have lots of additional features in our language, so we also have branching and selection, both at the type level and at the term level. We have recursion, right? So you can have cyclic transition structures as well. We have if and let, so ultimately this program calculus is Turing complete. And we have something called skipping. Now, skipping is quite an interesting phenomenon. It's the idea that if I am Carol, right, and I need to be typable by some type G, but this G has only a single transition labeled with a communication from Alice to Bob, right? Being Carol, I am not involved in this communication. So for me to be typable by G, basically I should just skip this transition and show my typability against G prime. That is the idea of skip. Now, in this very simple example with only one transition, this is easy, but if you have arbitrary branching in your transition structure and recursion or cycles as well, then it gets a lot more complicated. And so the most difficult typing rule for us to get right was actually the one that supports this kind of skipping. For people who've seen multi-party session types before, this is very much related to merging in the classical approaches. Okay, we do all these 4 steps, and yeah, then we can write the paper, submit to POPL', and then we are happy. That is sort of, in a nutshell, what happened here. Okay, there's one last thing that I want to discuss. I am now, I would say, finally in a position to sort of highlight what I believe is the most interesting novelty, technical novelty of this work, which is that the typing rules of our system are what is sometimes called synthetic. And synthetic in this context means that in our typing rules we have meta variables that appear in the premise of the rule, but not in the conclusion. So to give you an example, this was the typing rule for output processes, right? We type it with G. Then from G, we synthesize G prime, and then we use G prime to type P prime, but G prime itself does not occur in the conclusion. And this is very different from most of the typing rules in the existing multi-party session types literature, which are what is sometimes called analytic. Analytic in this context then means that each meta variable in the premise also occurs in the conclusion. And in particular, if you look at this, let's say, representative rule for output processes in the traditional multi-party session type sense, then we still see that P prime needs to be typable by, well, in this case, local type L prime, but that's not really the point. It still needs to be typable by L prime, but this L prime, it syntactically already occurs in the conclusion of the rule, which reinforces somehow the idea that in these existing type systems, you're very much syntactically matching the type against the term to establish typability. Okay? Fine. This is a very technical property in some sense. Why does this matter? Well, we can make two observations now. The first observation is by synthesizing the G prime from G as part of the premise, but not the conclusion. The syntax of G itself, or the structure of G internally, it doesn't matter at all. We care only about the transitions of G, and whether or not this is a global type or a configuration of a Petri net, we really don't care. Right? And then the follow-up observation is that, yeah, if we don't care about the internals of G, then we can basically just treat it as an opaque state of a label transition system. And once we made that observation, we sort of thought, okay, that's kind of nice. Can we formulate the whole meta theory in terms of arbitrary label transition systems? So, arbitrary label transition systems, well, the arbitrariness, that turns out to be a bit difficult because we need to know at least some things about the transition structure. And so we defined a number of, let's say, sanity conditions that each such an LTS should satisfy, which we call together well-behavedness. Now, I don't want to go into the details of what those conditions exactly are, but the things that you can think of is, for instance, we need some kind of confluence, we need some kind of determinism, we need them to be finite, those kind of things. Okay, fine. But you can define this, well-behavedness. And then the main theorem is that we have progress and preservation for states of well-behaved label transition systems. So at this point, we no longer care about where G exactly comes from or what it is. No, it can be just a state in a transition system. This is the general case. And then for the special case, we separately prove that if such a G happens to be a global type, then the transition system that you can generate for G using the existing operational semantics in the session types literature, those LTSs are well-behaved. So this progress and preservation result, it does carry over from the general case to the special case. And that's essentially it. This is again the slide with the contributions. I won't go through them in detail again. There's some future work I can mention, but I think I ran out of time, so let me not do that. Thank you for your attention.
Thank you very much. I think we have time for a question, but if the next speaker could start setting up, that'd be great.
Can you formulate progress and preservation as a simulation property?
I think yes. I think yes. We haven't tried it, but it is very close to a kind of simulation, yes.